Hi everyone. In this video, I want to tackle a problem with you, which consists in writing a problem in a dimensionless formulation. So in most of the problem that we meet, we have to solve an equation that is given in physical quantities or coordinates. And if you want to perform, especially if you want to perform a asymptotic analysis or perturbation analysis of the problem, it's very important to work with dimensionless numbers. And make sure that we can recognize, in our case, the existence of one or two or maybe three small numbers. All right, so to do this, I want to just start with an example, and then we will practice these types of skills during the different chapters as we meet new problems. All right, so the question is, we have a differential equation, or it could be an algebraic equation to start with, which is written in terms of physical quantities or coordinates. And what we want to do is to rewrite that equation in a dimensionless manner. All right, so to do this, the exercise or the example I've considered here is an example that is quite simple because it's governed by a simple differential equation. You see, it's a three-term equation. It actually consists in the bending deformation of a slender beam which rests on two supports, and it's also resting here on a foundation that is slightly flexible. The stiffness of the foundation is K, while the bending stiffness of the beam is EI, Young's modulus and second moment of inertia. All right, so the units of those quantities are reported here. K, this is the stiffness expressed in newtons per meter, but this is distributed along the length of the beam, so we have newtons per square meter. The bending stiffness is newtons times square meters. Another quantity is the transverse displacement V in meters. And we have on the right-hand side, we have the load that is applied on that beam. And so based on that load, the beam deformed in a certain configuration. We assume here that the bending stiffness EI is a small number, and we would like to determine the deformed configuration here, which actually could look like this, the deformed configuration of that beam, which is characterized by the displacement V as a function of curvilinear abscissa x measured from the left end. All right, so there are a few rules to change the formulation of the problem and come to a dimensionless formulation. First, you need to observe, of course, that this original equation has units. The units of the original equation is newtons per square meter. All right, so per meter. So that's something important. So first, observe units of equation. Okay, depending on what the equation translates, if this is a compatibility, an equilibrium, a conservation of mass, the units of the equation usually are quite easy to get, all right? Or just look at the units of what you have in each term of that equation, and that's the problem is solved, all right? So first, observe the unit of the equation, which means that in our case, we have newtons per meter, which means that you'll need a characteristic quantity with those units. All right, so that's rule number one. Let me just put a few rules for you, and then we'll see if we can use these rules to write the dimensionless version of that equation. Second rule is first look at the unknown quantities and independent variables. All right, so look at scales for the independent variables. Well, in this case, there's only one, x, and the unknown of the problem. In this case, there's only one. This is v. All right, you could aim at solving a set of differential equation or a set of algebraic equations, in which case there might be several unknowns in the problem. All right, and for each of them, we need a characteristic quantity. Okay, for each of them, find or get, if you want, a characteristic quantity. Then third, use these to rewrite equation and use the freedom you still have to simplify the notation. All right, and then 4, there's an important rule which says never use small quantities or quantities that you would like to be expressed as small in the scaling. All right, not at first, not at first, maybe later. All right, maybe later. That's something I will discuss. Okay, so these 4 rules are definitely the only rules you need in order to rewrite the governing equation of a problem into a dimensionless formulation. All right, let's see together how we can do that. So I forgot probably to equip that differential equation, which is a 4th degree differential equation with 4 boundary conditions. Let me just write them over here. So we'll assume that the transverse displacement is equal to 0 at both ends of the problem. So we have V0 is equal to VL is equal to 0, and the same for the second derivative, like this. All right. And it means that all quantities we have in this problem are listed over here, right? We have a bending stiffness and a ground or soil stiffness here. We have the transverse displacement, applied load, and we have the length of the beam. All right, so we have 5 quantities, and what we shall start with is number 2. All right, find characteristic quantities for the independent variable x and for the unknown of the problem. All right, so start with finding characteristic values, and this is always where we start with. All right, find characteristic values for x and v. All right, so first look at the units, right? So the units of x are meters, and the units of transverse displacement are also meters. All right, so based on what we have in the original problem parameters, is there anything that is obvious and that can be used in order to determine those characteristic values? All right, so if we start with x, you see x is a curvilinear abscissa. In this case, it's straight, measured along the beam. And I believe it makes totally sense to use the total length of the beam in order to scale or to have a characteristic value for x. All right, so that's when you look at the problem as a whole, try to get a big picture, and the big picture for x is actually that x runs from 0 to L. This is the domain on which we solve the differential equation, right? So we're going to write that the characteristic value for x, I use a star to indicate this is a characteristic value, can be chosen as L. This is not the only way to determine characteristic length, and this is good, right? Because I don't want to have a characteristic length for the transverse displacement, which is also equal to L, right? Because this is a transverse displacement, and if it's transverse, this is a quantity that is first orthogonal to this direction. So probably this already hints this is not a great choice. But at the same time, the quantity by which this beam displaces transversely is something that might be, and hopefully is much smaller than the total span of this beam, right? So it means that we should probably seek a combination of these three quantities here. Of course, this one in the middle can be used, okay? Because we're looking for a characteristic quantity for V, so of course we cannot use V. We just said we don't want to use L, and so what remains is this set of three values. And so, for instance, if you compute the ratio of the first and the last, you see that you can produce a quantity that has units in meters. You could also, as another option, compute the cubic root of this divided by that. And that's also something that provides meters. And you could also compute the fourth root of EI over K, and that's also something that provides meters. All right, so at this stage, there might be different ways to define a characteristic value for V. And if you are unsure, of course, I know exactly what to do here, but I have not obvious or clear arguments right now to orient you without any of those three choices. All right, so we know there are three ways to do so, but among these three ways to find to work, I have no clear answer as to which one we should use right now. Okay, so if unsure, let me just write if unsure. Then just keep V star right now. Just keep V star right now and use later your freedom, okay, to fix it. Okay, and once this is done, use these quantities to rewrite the equation that you need to solve, all right? So we come back to the governing equation, and we're going to use those quantities. So first, before that, it means that we need to define dimensionless quantities. And if we define dimensionless quantities, it means that we need one for the independent variable, and so we're going to say that x is equal to xi times L. So when x belongs to 0, 1, it means that x in 0, L, it means that xi is in 0, 1. Okay, which looks already quite nice. And then for v, I'm just going to say that v as a function of x will be this characteristic quantity, v star, still unknown, or still free to choose, multiplied by a dimensionless quantity, y, which will be expressed as a function of xi of x. All right, or if you want to put it in a different way, this is y of x over L. All right. And so now we need to use these two things and substitute them in the governing equation. All right, so the governing equation, copy. Let's put it here. What do we have? EI multiplied by the fourth derivative of v with respect to x. All right, so we're not going to, well, you see now because v is a function of y of xi, somehow I can write it like this, v y of xi. I would just write that derivative with respect to x is equal to a derivative with respect to xi multiplied by the derivative of xi with respect to x, which is 1 over L d over the xi. And we repeat this 4 times. So we'll have 1 over L to the power 4 multiplied by v, which is v star, multiplied by the fourth derivative of y as a function of xi of x, of course, all right? So this is not a smart way to write. I should write it like this first, and then I will rename this quantity. I will just rename it xi. All right, and so what do you observe over here is you observe indeed that the fourth derivative of v with respect to x is something that has units of v divided by units of x to the power 4. Characteristic value of v divided by characteristic value of x to the power 4. All right, and so it totally makes sense, and this has no units anymore. All right, this is unitless. All right, so what we have is EI multiplied by V star over L to the power 4 multiplied by the fourth derivative of y plus k times V star times y of xi, and this is equal to P on the right hand side. All right, so P is the applied load, which is also expressed now as a function of xi. All right, all of these are functions of xi. Okay, what could we do here? We could observe that the right-hand side P, this is something that has a certain order of magnitude, and definitely we will have to use this in order to define the right quantity for V star. Why do I do that? Because if I consider rule number 4, I just observed that I should never use a small quantity in the scaling, at least at first. And what we want to say in this problem is that there is a dimension, there is a small bending stiffness here, so I should definitely refrain from using EI in the definition of any scaling, all right? So it means that the scaling needs to be something that is achieved by means of the balance of these two things. So it means that we should have a little bit closer look at the order of magnitude of P. And for instance, I could just define P as P star, which is a characteristic quantity, multiplied by pi, which is a dimensionless quantity, and which is of order 1. All right, so we just write pi is of order 1. Okay, in which case we see that this equation here can be rewritten by dividing everything left and right by kv star. All right, and if we do that, we have EI, V star simplifies out, we have k, L to the fourth derivative of y plus y is equal to P star over K V star multiplied by something that expresses the distribution of loads across the element. All right. And so once we have this, then we can use our freedom in order to simplify that equation. And for instance, here on the right, this is my choice. I can definitely do this. I will just choose V such that this is equal to 1. All right, and if this is equal to 1, it means that V star choose V star as equal to P over K, the stiffness. All right, and the units are newtons per meter divided by newtons per square meter. All right, so we are fine. In passing, you see that what I did here is I divided the equations by K V characteristic, which has the units newtons per square meter multiplied by meter. So which has the units newtons per meter. And these actually correspond exactly to what we started to observe the equation, the units of the equation. And so the characteristic load or force, transverse force that is applied on the structure actually is given by K times V star in that formulation. All right. And then what's next? What's next is to have a look at the small numbers. And we know that EI is a small number. Small compared to what? We still haven't said compared to what it is small. If you want to make sure this is a small number of the problem, in fact, EI needs to be small compared to KL over 4, to the power 4. And in that case, it means that indeed we might be able to determine an asymptotic solution of the problem and use a small parameter, all right? And the small parameter that we would define is epsilon is equal to EI over KL to the 4. And this is a small quantity. Okay, in this problem, we'll see later when we'll deal with this problem and we will want to solve it. In fact, we will realize that it's much easier to define epsilon to the power 4 over there, which makes it a little bit nicer in the equations at the end. All right, this is a problem where we'll find a boundary layer, which seems quite unusual in solid mechanics, but definitely this is exactly the same behavior as the boundary layers we know from fluid mechanics. All right, so at the end of the day, the equation that is rewritten in terms of dimensionless quantities is just written like this, is equal to pi over xi, and the boundary conditions will be y when x, which means xi is equal to 0, or xi is equal to 1, these two are equal to 0. These are the two boundary conditions over there. Now we need to rewrite the second derivative. The second derivative will introduce a 1 over L square, all right, based on this chain rule differentiation. Okay, we can get rid of that because this is equal to 0. And in the end, we'll have that the second derivative, when x is equal to 0 or 1, both of them are equal to 0. And that's it, all right? So we have rewritten the problem in a dimensionless version, which is apparently much easier than the original problem we had to solve. At least you can read the problem easily and make sure it is solved with a minimalistic number of quantities. All right, so now whether it was obvious or not to choose the combinations we used for the characteristic loading, for the characteristic small bending stiffness, or even for the characteristic transverse displacement, is something that should come naturally, especially if you follow this flow chart, starting first by finding characteristic quantities for the independent variables and for the unknown problem. If you can choose, or if you can set everything, do it. But if you're not sure you can find, then keep it free and use your freedom a little bit later. And you will see that this should come naturally. The equation should bring you to a format that is quite simple. All right, and so returning to the original original discussion that we took over here, we just realized that the transverse displacement is indeed characterized by P and K. These are the two quantities that we should use in order to define the characteristic displacement, all right? Which is anyway the only option if we want to discard the use of the small number in the scaling, all right? Probably that's something you thought of. All right, so let me just tackle another problem, which is exactly the same, but let's assume now on top of the elastic restoring forces, all right, in the beam and the external applied loads, let's assume we have some dynamics, and let's assume we have also inertial loads or inertial forces. All right, so if we do that, then problem 2, the governing equation, they become something like this: second derivative with respect to time of v plus ei, fourth derivative with respect to space of v plus k times v is equal to p of x and time t. All right, so what we did here is that we have added the first term in that equation. And so let me just copy the quantities we have over here. Copy and paste so that we can just add in the list. We can just add time. All right, so we have time, t, in seconds. That's what we need to construct. And we have space in meters. And what I'm going to do here, I will put together all quantities, transverse displacement in meters. All right. Okay, so if we want to revisit the problem here, then what we're going to do is that we need for x, we need a characteristic quantity, which of course will still be the length of the beam. We'll have a characteristic quantity for time t, and we'll need a characteristic quantity for the transverse displacement. All right. So probably the characteristic quantity for the transverse displacement can be chosen as the same as the one we had before. And now for characteristic quantity with respect to time, we need to construct a characteristic time based on that. And so as a matter of fact, what I wanted to do here is to add the mass per unit length. And you see that the mass per unit length, if you express the mass as a force over acceleration, this is what we get for the mass per unit length, right? And so by combining, again, exactly as what we did before, by combining this together with that, or together with this, or together, but probably not, because this is a small number at the end of the day, we can combine it with this in order to get rid of the newtons, and hopefully as well use a length somewhere in order to get rid of the meters, and then we end up with a characteristic quantity that can be used as a characteristic time. All right, but as I don't want to decide right now whether I'm going to use this one or that one. Although that might be obvious for you that we're going to keep P as a right-hand side. So this is a forcing. That's something that does not necessarily describe the system that we want to study. So it's really highly likely that what we want to keep is a characteristic or a quantity which is related to the system itself, so the stiffness. All right, but I just want to show you that this should come naturally from the equations. All right, and so let's keep momentarily T star as a known, and let's probably fix for V. Let's fix P. Let's take a characteristic value of the applied load divided by the stiffness K. All right, and so if we do that, we can rewrite the equations. What does the second derivative of V with respect to time t become? If we follow the same thing as what we did earlier, you see that we're going to have a second derivative with respect to time, which is going to bring in the denominator, is going to bring the square of the characteristic time, and in the numerator, we'll have the characteristic displacement. Okay, so it means that the first term of the equation will just be second derivative with respect to time of the displacement. All right, so let me just write this d tau of y, and I will define a dimensionless time tau just by saying that the time t is tau times t star, or in other words, you can put it this way: this is time t over t star, exactly like we have xi is equal to x over x star, which is x over L. All right, then second term will be EI. We need to copy what we did earlier. EI times the fourth derivative. All right, so that's going to be EI multiplied by the fourth derivative with respect to space. That was the second derivative with respect to time, plus k times y is equal to, k times v star times y is equal to p star times pi. All of them right now are functions of xi and tau. All right, same here, functions of xi and tau, because this is a partial differential equation now. All right, and so, of course, if we choose again V, characteristic V as P over K, then we see that K times V star is again our characteristic force per unit length. And we can divide left and right by that quantity. Okay, so if we do that, we have mu multiplied by V star, which actually drops, divided by K, T star square, second derivative of Y, plus EI over K L. Okay, I use L to the power 4, I'm sorry. This was x characteristic, of course, here to the power 4. Then fourth derivative with respect to xi plus y is equal to p star over k v star times pi. All right, so what do we do here? Same as what we did earlier. Choose our freedom in such a way that this is equal to 1. This will be a small quantity, so define this in such a way that it's going to be equal to epsilon to the power 4. All right, and then we ended up with something here, and I would say again, use our freedom on T star, in such a way that this is equal to 1. All right, and so the equation that we want to solve is second derivative with respect to tau plus epsilon to the 4, fourth derivative with respect to xi plus y is equal to pi over xi and tau. And the boundary conditions are very similar to what we had earlier, and there should be an initial condition here because we have a derivative with respect to time. All right, so it means that the characteristic time that we needed to choose, t star, is in fact nothing but the square root of mu mass per unit length over k. And this is something related to the natural period or natural period of vibration. Of a string, so it's not a beam, it's something that has no bending stiffness. It could be a cable if you wish, of a string laid on distributed springs. So I don't want to say this is exactly the natural period of vibration. In any case, there's just not only one. There's a bunch of them. Could be the fundamental period of vibration, which is not a case. There should be a factor pi between the two of them. It's just a order of magnitude, all right? So it just scales with the natural period of vibration of the string, and this is how we can choose it, all right? And so you see that if we come back to what we said earlier, the characteristic time scale is obtained by combining these two quantities, and that's pretty it. You see, Newton and square meters, Newton and square meters. We didn't even have to use L, so the span of the beam, in order to determine a characteristic time. All right, so this being said, you see that we can transform differential equations using this principle into forms that are much simpler than what we had before. And so in classical textbook, in perturbation methods, usually the equations that you solve are already written in a dimensionless formulation, but that's quite important for you to be able to come from the physical problem you want to tackle or you want to solve and go down to this simplified version of the equations. All right, a bit later in the following videos, you will see that sometimes rescaling will be necessary. And if we do rescaling, it means that we change the original scaling of the problem. All right, so it doesn't mean that this is the end point, doesn't mean that this is the final version of the equation you have, but at least this is where you should start to have a first look at the solution as a big picture. All right, and so now in the following videos, we will see how we can solve those problems globally, and then use rescaling to find local solutions in those problems. All right, so I hope you enjoyed, and keep going with the following. Have a nice day. Bye-bye.